Today we're going to look at double replacement reactions. So with single replacement reactions, we always had a pure element and a compound. With double replacements, we have two compounds trading partners with each other. So let's look at an example. Here we have AgNO3, which is silver nitrate, and NaBr, which is sodium bromide. One thing that's going to be really important in a double replacement reaction is to know if everything is aqueous and dissolved in water or solid and not dissolved in water. We're always going to start out with two aqueous compounds, but if you check the solubility rules, you'll see that AgNO3 and NaBr are both soluble in water and therefore aqueous. When we write the formulas for these, we don't show the fact that there are charges present, but there really are. They are ionic compounds. They're made out of a positive and a negative ion. So for example, AgNO3 is made out of a positive Ag ion and a negative NO3 ion. Similarly, sodium bromide is made out of a positive Na ion and a negative Br ion. Keep in mind that these numbers could be positive 2 and 3, but I chose ones because it just makes things simpler for this first example, but you will have to keep them in mind as we move forward. Anytime we look at a double replacement reaction, what we want to see is that the two positive ions trade places with each other. Once we've come up with new partners for them, though, we do need to do a crisscross again. Again, I've chosen all ones, so it makes it pretty simple, but we get NaNO3 and AgBr here. Once we have our two products, what we need to do is check their solubility. So if you look at your rules, you'll see that all Na compounds are aqueous with no exceptions, so NaNO3 is aqueous. AgBr, on the other hand, is a solid. So this is our precipitate in the reaction, the solid that's formed. So our overall reaction here, when we write it out, is aqueous AgNO3 plus aqueous NaBr yields aqueous NaNO3 and solid AgBr. And that's our precipitate. That's the important thing we're looking for here. As a matter of fact, that's the main thing that we're looking for in these reactions, at least at this stage, is the formation of a precipitate. So in general, this is what we're looking for. AQ plus AQ gives AQ plus solid. Of course, the AQ doesn't have to be first. You could put the solid first. Doesn't make a difference. It's still addition. But the thing is that we're looking for that solid precipitate. So let's look at an example of when a reaction does not occur. And that's basically when we don't form a solid. And here's why. Imagine we've got, again, that AgNO3 and it's aqueous. We draw it and we write it as if it's one thing. But when you dissolve something in water, remember that the positive ion is stabilized by water molecules and the negative ion is stabilized by water molecules. So they basically are totally separate from each other and just kind of floating around as separate ions, even though we draw them and write them as if they are one thing. When we write something as solid, though, those things really are stuck together. The positive and negative are balancing each other. So solids really are the way we write them. So let's look at KNO3 plus NaBr. Again, we know that they're each made out of ions, and I've just chosen ones because it's simpler. We have our positive K and our negative NO3, our positive Na and our negative Br. You can check that they're both aqueous, but again, all of our reactants are going to be aqueous at this stage. Because they're aqueous, again, we know that really those ions are not in contact with each other. They're floating freely and separate from each other. Look at them go. So when we go to do our step where we trade the positive ions with each other, we can do that. And then we can look at our results and we can do our crisscross to get our final compounds. Now when we look at the solubility, we see that both of these compounds that we got are aqueous. So we started with two aqueous compounds before and two aqueous compounds after. So aqueous KNO3 plus aqueous NaBr yields aqueous NaNO3 and aqueous KBr. But that means that beforehand, we just had these four ions floating around separate and independent from each other. And afterward, we have the same four ions floating around separate and independent from each other, which means that nothing really happened here. So we cross out the arrow and we write no reaction. And we'll do that every time we get two aqueous products during one of these reactions. So again, what we are looking for here, we always have to have a precipitate. Otherwise, no reaction actually occurred.